Welcome to my presentation on the paper Is Vanilla Policy Gradient Overlooked? Analyzing Deep Reinforcement Learning for Hanabi, which is a cooperative card game. It's very interesting, I think. This paper was published in the Adaptive and Learning Agents workshop of AMAS 2022, together with my co-authors Jelle, Maurice, and Jim, who supervised me throughout this project. So first I'll go into the game Hanabi, the card game, and how you play this and why it is interesting. Then we'll go into the experiments, comparing the different algorithms that we tried out. And then we'll analyze a little bit deeper what happened under the hood with the policies of these algorithms, and we will conclude. So first, Hanabi, how do you play this game? It's a cooperative card game, uh, which you play with 2 to 5 players, and the goal is to score the highest score possible together as a group. And you do this by building these fireworks. For every one of the 5 colors, there is a stack that starts with a 1, and you have to build it all the way up to 5. If you finish all the 5 fireworks, as they are called, then you have a score of 25. So there are many different cards in this game. Each have a rank and a color. So a rank from 1 to 5, and one of the 5 colors: blue, red, white, green, and yellow. Now the trick of this game is you hold the cards the other way around than you're used to. So you can't see your own cards, but you can see all the cards of all the other players. So you have to cooperate to know what you can play. So every turn you have to do one of 3 things. So either give a hint to another player, saying, hey, you have 3 blue cards and they are this one, and this one. So the hints are kind of restricted. You have to either choose a rank or a color and then point at all the cards with that property in one other player. And these 8 blue hint tokens that you see here, that budget goes down every time you give a hint. But luckily, if you discard a card, meaning we don't need this one anymore, then we get one of these blue hint tokens back. And discarding can happen because there are many duplicates in the game. Only the 5s are unique, but the other ones all have a duplicate, and the 1s are even in the deck 3 times for every color. And then finally, of course, you can also play a card. So if you think, well, I think this card is playable right now. So for example, in this situation, a red 3 would be playable. And then you put it on the table, and if it fits, that's great. The score goes up, and if it doesn't, we lose one of these 3 life tokens. So if that happens 3 times, the game ends. So if the 3 lives are lost, the game ends immediately and the score goes back to 0. The game can also end, of course, if you have a perfect score of 25, but mostly it ends when the deck is empty. That means that everybody else gets one more turn, and then the game ends and you count the number of successfully played cards to get your score. Okay, so why this game? Why would we attack this with AI? Why would we try this? Why is this interesting? Well, actually, there's this paper called the Hanabi Challenge, which called this game a new frontier for AI research by Nolan Bard et al., a group from DeepMind. And they have a few pointers into why this is an interesting game. First of all, it's a multi-agent setting, of course, but it's also a cooperative game. So we want our AIs to be able to cooperate well with humans, hopefully. And it's partially observable, of course, because you cannot see your own cards. And so, yeah, the long-term goal is that AIs might be able to understand intentions and beliefs of others, other agents, or even humans, on what they are doing, specifically in this game about their cards, and what other agent might be doing for the next action. So a little bit about the state of the art. It really depends on with how many players you play, and also in what domain. So by domain, I mean self-play is the first one. That means you play with copies of your own code, your own algorithm. And you see that in the 3 to 5 player regime, the rule-based agents are still the best. We use a smart tactic called the mathematical hat game strategy. And and they score almost perfect scores, as you see. But in the two-player domain, this strategy doesn't work really well, so deep reinforcement learning has been able to surpass the state of the art there. In another domain called ad hoc, you have to be able to play with any kinds of different players. So in a way, this is much more interesting, but it's also much harder, of course. And scores are also very difficult to measure because you have to measure with a lot of very diverse set of agents to be able to determine what your contribution is to the score. And some tests have been done with many other agents and many humans as well, and they score about 15. So there's a lot of room for improvement still. Now, in our research, we used a simplified version of Hanabi, which means that we made it actually fully observable. So we did see our own cards. This made it much easier, of course. Um, and we only restricted ourselves to the two-player regime and also in self-play, which most of the papers are in right now. So let's go into the experiments. First, a little bit about the setup and what we are comparing. So we will look at three algorithms: simple policy gradient, vanilla policy gradient, and proximal policy optimization, PPO. Um, the first two are very similar, except for the fact that vanilla policy gradient has two networks. So simple policy gradient is actually very similar to the reinforce algorithm by Williams, and it only uses one network, a policy network. And while vanilla policy gradient has also a value network, so it can use this advantage function here in the objective. These are the three main objectives of the actor networks, and this is where these three algorithms, they are all on policy where they differ the most. You see that PPO has a completely different objective than SPG and VPG, and it includes this clip function, which means that the update has to stay close within the policy space. So a little bit about the reward shaping that we used. These are the standard rewards, of course. You get a +1 if you successfully play a card, and the score goes down to 0 if you lose all your life tokens. What we used furthermore is we gave a punishment for illegal actions. So for example, you're not allowed to discard yet if your hint token budget is already full, and the algorithms needed to learn this. You could also mask this, but this gave us some trouble sometimes, so we decided to let them learn the legal actions. And we also used a bit of other extra reward shaping to be able to say we want you to play more, or we want you to discard the right cards, etc. Also a little bit about exploration. In our first experiments, we noticed that our policy was becoming deterministic quite fast, which means that the output of the action probabilities is a lot of mass is on one action already quite early in training. And this can be okay if you choose the optimal actions, of course. But it happened quite a lot even for non-optimal behavior. So we wanted to stimulate the exploration a little bit more, which we did by using an entropy bonus. So we include the entropy of the policy and with a certain coefficient, which we set to 0.01, I believe. You can view all of our hyperparameters in the appendix of the paper. Yeah, let's go to the results. So here is our main graph. It shows the learning curves of all the algorithms. We've run them for 5 seeds, and we take the average line. You also see the standard deviation shaded. And on the y-axis, we have the score. On the x-axis, the epochs. Every epoch had about a batch of, every epoch is one batch of 1,000 time steps. So you see that we've run it for a quite long, 2.5 million epochs, or 2.5 billion time steps. Which also shows that these on-policy algorithms can be quite not so sample efficient as they are known. And as you see, PPO, the red line is the first to learn. but it actually hits a plateau at many different levels, we'll see. So VPG, the vanilla policy gradient, is actually able to surpass it in this benchmark. Here you see all the separate runs, and it's visible that PPO is hitting different plateaus for different seeds. So yeah, while the other two are much more stable to the different seeds that they are getting. So a little bit into the analysis. We looked into the average policy that was outputted at the end of training by this graph is for vanilla policy gradient, our best performing one. And we look only until the first 10% of training right now, so 250,000 epochs. And you see that at about 50,000 epochs, there's a switch point where instead of playing a lot, which is it's probably in the beginning it was doing very not so carefully, so just playing cards and losing lives, it all of a sudden turns towards a much more conservative policy, you could say, being much more careful which cards it plays and slowly growing the play actions up again to be the correct ones. And this one keeps growing even towards the end. You can see it in the appendix. And you can also see this in the life tokens that are kept towards the end of the game. So here at in the y-axis you see the average amount of life tokens that are left over at the end of an episode. So if that is 0, it means the score went all the way back to 0, which is what happens a lot at the beginning of training. And you see that you need to retain at least one life token to, oh, sorry, one life token to have to keep your score. So you see that PPO is actually the first one to discover this, and then vanilla policy gradient comes after that at around the same moment that the policies switch, as you see here. And simple policy gradient is much slower. Now we can also look into the policy probabilities per different action. So here in the previous graph we grouped the play actions and the discard actions, but here we can actually say, well, which card did you actually pick? Because you have 5 cards in your hand, and here we can see from which position the agents were actually playing or discarding, and the H stands for hint action. You don't really need a hint in the simplified version of Hanabi, but we still included it because to avoid these illegal actions, you need to be able to hint to discard later on. And it can also be used as a sort of pass action to give the turn to the next player. But what's interesting here is that P4 is used a lot. So the last index of your card position is used a lot, which might make sense because that's where the new cards come in. So every time you play a card, all the cards slide up one spot, and then the newest card is added to the end, which means that if you get a new card, it might be directly playable, and you can play it immediately. And the discarding is much more spread out with a higher entropy, you could say. You're also keep track of the entropy, of course, during training. And we see actually that PPO has the lowest entropy. So it is the most deterministic, like you could say, even though it was not performing best. So being a little bit more spread out might be good, which vanilla policy gradient has, the green line. And simple policy gradient, yeah, is just doesn't really know what it's doing. Well, it does actually, but with a much higher entropy. So let's go to the conclusion. This is the main graph again. So what we saw is that PPO is very quickly able to learn, but it can hit a plateau, making the option available for vanilla policy gradient to surpass it in performance. And our hypothesis is that this clipping operation in the objective function might have to do with this, because PPO is restricting itself from staying. It has to stay within a certain area of the policy for each step, so it might get stuck in a local minima or maximum, I should say. Yeah, so thank you for listening. The code is available on my GitHub. And if you have any questions, I would love to hear them at the Q&A session, which is coming up. And you can also email me here. Let me shortly show you the GitHub after I've shown the references. So this is my GitHub page where you can clone the code, and then after installing, you can even play with one of our pre-trained agents. I will quickly show that here. So for example, right now I want to play my last card. So I say B5, and that finished a perfect game. So I hope you have a lot of fun playing with our agents. Thanks, and see you hopefully at the workshop.